So we came to the realization that a body is said to be in a uniform circular motion when the body moves, okay, at a constant speed within a circular path. So circular motion is the motion of a body within a circular path. Okay, and we made mention of examples of motions we can describe as circular. And please, can you share with me examples of circular motion we made mention of during our meeting? Some examples of circular motion. Anybody? One or two? Michelle?
A roller coaster.
So the motion. So Michelle, here use the motion of a roller coaster. Okay, because
Yes.
if the coaster or roller coaster doesn't move, it wouldn't describe a circular motion. Leslie.
Please, a cyclist negotiating a bend.
A cyclist or a car negotiating a bend. Okay, it can even be an athlete running in an oval. Then we also talked about the motion of electrons within the nucleus, around the nucleus in within the atomic shells, the motion of planets around the sun, the motion of an object or a stone tied to a string and then whirled. So we have several examples of motions we can describe as circular. Okay. Then we pick a body in a circular motion. Assuming this is the center of the circle, O, we connected the position of the body. The body is here, the particle is here at a point A. When it moves within the circumference from one point A to another point, so the new position of the body. This displacement of the body within the circumference we term as the linear displacement. So A to B or AB is a linear displacement S of the body. Now the initial position A, the final position B can be connected to a certain angle described at the center. So we can connect this position of the body to an angle described by the radius. Of course, this is the radius R. So as the body moves from A to B, it appears it is the radius that is being moved from A. Okay, so the radius seems to be sweeping this angle as if it's a metal rod that is being connected, okay, between O and A. We can also picture this to be the blade of a fan at the center and at one point. Now you hold the blade of the fan, push it to sweep a certain angle. Okay, so as the object moves, we realize that it's as if the radius is sweeping a certain angle at the center. And this angle swept at the center by the radius is termed as the angular displacement. So theta. So while the body moves within the circular path, the radius of the circle also seems to sweep a certain angle at the center. When the body is at C, it's as if this radius, which is initially at A, sweeps this angle and then gets to C. So the greater the displacement of the body within the circumference, the greater is the angle swept by the radius at the center. So we saw a relationship between this duo, which is the linear displacement S and the angular displacement at the center are directly proportional to one another. Okay, because as the linear displacement increases, we also see an increase in the angular displacement at the center. When the body manages to move from A to, let's assume this point D, the body has gone through half of the circle, semicircle. So from A, which is half of the circumference, becomes the linear displacement of the body. And look at the angular displacement, a whole angle of 180 degrees. When the body goes through one complete revolution, starting from a point A and then comes back to a point A, it has gone through a linear displacement which is equal to the circumference of this circle. And the angular displacement at the center is also equal to 360 degrees. So we realize that S is directly proportional to theta. Okay. Please, when you join, please mute yourself for us. Come here, let me mute all so that. So if S is directly proportional to theta, then S is equal to a certain constant of proportionality times the angular displacement theta. Okay, and this constant of proportionality K is equal to the radius of the circle. And so S is equal to R theta is the equation linking linear displacement S and angular displacement theta. We also deduce the SI unit of angular displacement. As for linear displacement, we are used to the SI unit, which is meter. But what did we say? Okay, is the SI unit of angular displacement theta? What's the SI unit of angular displacement? Theta. Yes, anybody? Anybody to share with us? Yes, Leslie.
Please, radian.
It's radian. So the SI unit of angular measurement is the radian. Radian, shortened as rad. So please, when you are saying it, it must be radian. When you are writing it, you must shorten it as rad, R-A-D. Okay. Now, please, a minute to, okay, the call has even started. Okay. We realize that one revolution, one complete revolution, one rev is to an angle of 360 degrees, and this is also equal to an angle of 2 pi radian. How did we come by this connection? When a body goes through one complete revolution, any linear displacement within the circumference is given by S is equal to R times theta. And the circumference of a circle is given by 2 pi times the radius. So when the body goes through one complete revolution, start from a point A and ends at a point A, the linear displacement S is equal to the circumference of the circle. So if S is equal to C, when we compare, this R will be equal to this R, or yes, R will be equal to this R, and theta will be equal to 2 pi. So when the body goes through one complete revolution, the angular displacement theta is equal to 2 pi radian, which is also equal to 360 degrees. Please note that angular displacement in radian can be expressed in multiples of pi as in this case. This is 2 times pi. It can also be 2 pi radian. 2 pi radian. It can also be expressed in decimals. If we express this in decimal, then we substitute the actual value of pi, which is 22/7. And so this would give us 2 points. Please calculate this for me. 44 divided by 7. 44 divided by 7. Anybody? Okay, time is in. Okay.
6.2.
Okay. Okay, so 6.283. 228, okay, 6 radian. So angular measurement in radian can be expressed in multiples of pi or in decimal. So 2 pi radian is also equal to 6.286 radian. Now, if 360 degree is equal to pi radian, 2 pi radian, then of course 180 degree would also be equal to pi radian, which is 3.142 radian. You can do that for 90, which we did. 45, 30 degrees, 60 degrees, 15 degrees. So this is what would help you in changing angular measurement from degree to radian. Okay. Then we also realize that as angular displacement of the body in circular motion changes within the circumference with respect to time, linear displacement also changes with time. So a body moves from A to B, A to C, A to D. Then we realize that A to B, the angular displacement theta, A to C, the angular displacement is greater than A to B. A to D, angular displacement is greater than A to C. So as S changes with respect to time, the angular displacement at the center also changes with respect to time. Don't forget, in this case, the radius will not change. The radius is always constant. Okay. The radius is always constant. So as linear displacement within the circumference changes with respect to time, angular displacement at the center will also change with time. And so this gives us the relationship between the linear velocity of the body, or the linear speed, okay, of the body within the circumference, and then angular velocity. So S over T, which is displacement over time, gives us velocity, is equal to the radius of the circle times the rate of change of angular displacement, theta, with respect to time also gives us what is known as angular velocity or angular speed. So angular velocity omega is defined as the rate of change of angular displacement with respect to time. The rate of change of angular displacement with respect to time. And its SI unit, because angular displacement is in radian, time is in seconds, the SI unit of angular velocity is radian per second. Radian per second. So this gives us the length between linear velocity and angular velocity. Other units of angular velocity can also be revolution per second, shortened as RPS, and revolution per minute, RPM. Then revolution per hour, RPH. Okay, but note that the SI unit is radian per second. Please, is there any question? Okay, today let's move on to another important section known as angular acceleration. Angular acceleration, represented by the letter alpha. The angular acceleration of a body executing circular motion. So, what is linear acceleration? Linear acceleration is the rate of change of linear velocity with respect to time. So, acceleration, as we know in linear motion, is changing velocity over time. Okay. Implying that angular acceleration, look at something. We said angular velocity is the rate of change of angular displacement with time. So omega s delta theta over t. Therefore, angular acceleration alpha would also be the rate of change of angular velocity or angular speed with time, with respect to time. Okay, so angular acceleration of a body in circular motion is defined as the rate of change of angular velocity with respect to time. I'm taking it again. Angular acceleration is defined as the rate of change of angular velocity or angular speed with respect to time. So delta omega over t. Can somebody help me deduce the SI unit of angular acceleration? The SI unit of angular acceleration. Can somebody help? Elizabeth.
Yes, please. Rad per second squared.
Elizabeth, when you are saying it, say it as radian. When you
Yes,
are
please.
writing it, rad, R-A-D, okay?
Yes, please.
Okay, so since angular velocity is radian per second, then time is in seconds. The SI unit of angular acceleration will be in radian per second squared. Note that other units can also be revolution per second squared, revolution per minute squared for you to convert, and even degree per second squared. I'll be sending you questions on this in order to, apply how you can work out the conversion. So take notes. All right. Then we've seen a relationship between linear motion, linear displacement s, and angular displacement theta. We have also seen a relationship between linear velocity and angular velocity. Okay, and since we are talking about angular acceleration, we must also deduce a relationship between linear acceleration and angular acceleration. So practically, look at something. If you on a fan, initially the velocity of the fan will be 0. But as the momentum of the fan increases, you realize that the speed will be increasing. okay, at the edge of the blades. When the speed of the blades increases, it means that the rotation, okay, at the center of the fan also increases. So when the speed of the blades of the fan increases with respect to time, it yields or builds up to linear acceleration at the center. As the angular velocity of the rod which connects the blades also changes with respect to time, it also gives birth to angular acceleration. Okay, so if we divide both sides of the equation by time, we have v over t given as linear acceleration a, and we have angular acceleration alpha equal to omega over t. So we have r times alpha. And this is the equation also connecting linear acceleration and angular acceleration. Note that all linear quantities occur within the circumference of the circle. So linear displacement, linear velocity, linear acceleration, they all can be determined within the circumference. All angular quantities are determined from the axis of rotation or are determined from the center of the circle. So angular displacement, angular velocity, angular acceleration can also be determined from the center or the axis of rotation. Okay. All right. Let's also understand two more important points. That is frequency and frequency of a body executing circular motion. Small letter f, and then period capital T. Can somebody share with me what frequency of a body in circular motion is? What is frequency as related to a body in circular motion? Either circular or rotational motion. Anybody? Mamiya?
It is the change in angular velocity with. No, it's the. It's.
Continue to try. Okay, Mamiya, still engage your brain. I'll come back to you. Leslie, okay, Refwa.
Yes.
Go ahead.
Please, frequency is the number of revolutions, or yes, number of revolutions with respect to time.
Okay. Thank you so much. So, as Refwa said, or Leslie, okay, doesn't matter. As was said, frequency of a body executing simple harmonic motion, circular motion, is defined as, I want to take attendance. Okay. A minute, I'm coming in. Let me share it on a platform before to indicate attendance today. All right, I think we can continue. Okay, so frequency, it comes from the word frequent. If you are frequent, okay, if you are frequent for an occasion or something, it means you go more often. Okay, so frequency of a body in circular motion refers to the number of complete revolutions within a given time. So frequency F is number of complete revolution divided by time. However, in most machines, we peg the frequency within 1 second. So within a time of 1 second, how many complete revolutions can be made? A typical example is that Akosombo Dam, the turbines at Akosombo Dam must be moved by the strength of the water so that within 1 second, the turbine must rotate within 50 to 60 times to give us the required voltage. Can you imagine? Within 1 second, the turbine must rotate 50 to 60 times. That's the frequency of the machines. The generators we use in our homes also have that to supply us with the required voltage. The generator must rotate 50 to 60 times within 1 second to give us the required voltage. So in machinery, the complete revolution is looked at within 1 second, but frequency is actually the number of complete revolutions within a given time. And another example is that Mamiya claims to be a very good athlete. Then I want her to actually prove me wrong. Okay, so Mamiya, if you claim to be a very good athlete, then I'm giving you a total time of 5 minutes. I want to see the number of rounds you can make, because she claims to be very good in 3,000 meters. Okay, so 5 minutes. Show me the number of rounds you could make. Maybe within the 5 minutes, Mamiya was able to make 3. So if I want to calculate how frequent Mamiya was, it is equal to the number of complete revolution 3 divided by the total time given. But this time we'll convert to seconds because we want to deal with SI units. So 5 minutes expressed in seconds will be equal to, what is 5 minutes in seconds? Quick one. 5 minutes in seconds. Anybody? Oh, you are wasting time. 5 times 60, 300. So we have 300 seconds. Good. So it means that Mamiya's frequency will be 0.01 per second. 0.01 per second. So the basic unit or the derived unit of frequency is per second, but it was added to Robert Hertz. And then, so the SI unit becomes Hertz. Okay. So that is frequency. Then period. Yes. Can somebody share with me what period of revolution is? A period of revolution. The period of revolution. Leslie.
Yes, please. Please, it's the time taken to complete one revolution.
Okay, so period is the time taken to make or complete one revolution. So Mamiya used 5 minutes to make 3. Mamiya used 5 minutes. The total time is 5 minutes or 300 seconds to make 3. If I want to calculate the time taken for each complete revolution, how do I determine that? In all, she used 5 minutes, which is 300 seconds, to make 3 revolutions. If I want to calculate the time she took to make one complete revolution, class, how do I determine that? Somebody should help. The time for any one complete revolution, how do I calculate that? Yes. Erefa.
Yes, please. Please, you divide the number of, or the total time taken by the number of revolutions.
Okay, so 300, the total time 300 divided by 3. Okay. So
Yes,
this will give us 100 seconds. What it means is that Mamiya took 100 seconds for each complete revolution. And that is the period. Okay. So the time taken to make that one complete revolution is the period of revolution. And so we can say that period capital T is given by total time divided by the number of revolutions. Total time divided by the number of revolutions. Okay, and frequency, on the other hand, is equal to number of complete revolutions divided by the time. Class, what is the SI unit of period? What do you think is the SI unit of period? Elizabeth?
Seconds.
Seconds. So it's a time. So SI unit is in seconds. Are we okay? Now, looking at the two equations, can we deduce a relationship between period and frequency? Period is T over small t over n. Frequency is n over small t. Can we deduce a relationship between frequency and period? Anybody?
Yes,
the gentleman, please help me out here. You've been quiet. The guys, you've been quiet. Looking at the two equations, can any one of you help me deduce the link between period capital T and frequency small letter f? Any one of you, the gentleman? Okay, ladies, somebody should help me out. If Lizzie?
And please, I think like frequency is the inverse of the period.
Exactly. That's the link. Okay. T is capital T, which is the period, is small t over n. F, which is the frequency, is capital N over T. So you could see that T is equal to 1 over F. If you cannot see it this way, make N the subject in each of the equations. So when we make N the subject here, we have small t over big T. If we make N the subject in frequency equation, we have N is equal to F times T. Let's equate both ends. So we have small t over big T is equal to F times t. T would cancel out, and we have f being equal to 1 over t, or t being equal to 1 over f. So when in questions, whenever you are able to find any one of these quantities, you can determine the other easily using this. Please, if you have any question, quickly ask before we continue. Is there any question? If you are not clear with something, let me know before we continue. Okay. So let's still consider a body going through one complete revolution and derive another important equation. Please, a minute. I'll get back. Okay, so when a body goes through one complete revolution, starting from A, going all the way and then coming back to A, its angular displacement theta at the center would be equal to, so when a body goes through one complete revolution, what will be the angular displacement in degree? What will be the angular displacement in degree for one complete revolution? Anybody? Yes, Leslie.
Please, is it 360?
Yes, in degree, one complete revolution is equal to 360. What will be one complete revolution in radian? What will be one complete revolution in radian?
Say 2 pi radian.
Thank you. So for one complete revolution, theta is equal to 2 pi radian. What will be the time taken to make one complete revolution? The total time to make one complete revolution. Anybody?
Please, capital T.
Thank you, capital T, because the period is the time taken to make a complete revolution. So if we determine the angular velocity omega, the angular velocity would be equal to theta over t. Theta for one complete revolution is equal to 2 pi radian divided by capital T. So for one complete revolution, angular velocity is equal to 2 pi radian over t. This class is very, very, very important relation in physics. We can equally express this as 2 pi times 1 over t. And we know what 1 over t stands for. 1 over t is frequency. So 2 pi times f.
They're downloading some files.
Okay. Now, please unmute if you haven't done so for me. Now, because frequency, because frequency is equal to number of complete revolutions over time, we can also express the same angular velocity as 2 pi times n over total time. These equations are so much used in circular motion, simple harmonic motion, wave motion, and even in current AC theory. Okay, so we use this equation so much in several areas in physics. So take note, angular velocity is equal to 2 pi over the period, or 2 pi f, or whatnot. Okay, let's quickly apply. I earlier sent, I think I sent a question, but only few of you answered it. The example 2. Let me re-forward it quickly and then we move on. Okay, so the question is that a toy train moves around a circular track of radius 0.5. So the radius of the circular track is 0.50 meter. Hey, how many radians has the train turned through in moving 1.4 meter along the track? Okay, the track is a circular track. So how many radians has the train turned through in moving 1.4 meters along the track? So we are given the angular displacement 1.4 meter. So in determining the number of radians, using S is equal to R theta, make theta the subject, and you have S over R. S is 1.4 divided by the radius, which is 0.5. This would give us I think 2.8 radian. So that's the answer for the A. B. What is the angle in degrees? What is the angle in degrees? This question sought to test your ability to convert angle in radian to degree. We know 2 pi radian, which is equal to 6.286 radian, is to 360. 2 pi radian, which in decimal is equal to 6 points. Let me write this well. 6.286 radian is to 360. So if we have 2.8 radian, will it be more or less? If 6.286 radian equals 360, 2.8 radian, will it be more or less? Class, would that be more or less? Anybody?
Less.
It will be less. If less, yes, the answer work has been answered. Thank you. If less, more divide. So because it will be less, we divide 2.8 by 6.286 and multiply that by 360. The radians will cancel out. That's why I'm not writing it. So What is 2.8 divided by 6.286 times 360? Please do that for me. Calculate that for me.
Sir, please is equal to 160.356 degrees.
So let's make it approximately 160 degree. So that is the answer for the B question. Okay. What is the angle in degree? So if you couldn't answer it, that's it. Then the second question. The minute hand on a watch is 6.40 millimeter long. The minute hand is 6.40 millimeter long, meaning this value must be the radius of the circle. So R is equal to 6.40 millimeter. Calculate its frequency. Class, tell me, at least we know that frequency is 1 over the period. Or frequency can also be number of complete revolutions divided by time. So how do we determine the frequency here? The minute hand on a watch is 6.40 millimeter long. A. Calculate the frequency. B. Its angular velocity. And then C. The speed of its free end. How do we determine the frequency? I put it to you. If you have the idea, share it with us. If you have the idea, quickly share that with us. Hey, the gentlemen and the ladies. Okay. Now, we don't have much time, so if F is equal to the period, when the minute hand goes through one complete revolution, what is the total time here? If the minute hand goes through one complete revolution, what's the total time? Or what will be the total time? Yansabua Kwaenko. Mami ya Elizabeth.
60 minutes.
60 minutes.
Yes, please.
Okay. If the minute hand will go to for one complete revolution, the total time will be 60 minutes. Let's change 60 minutes to seconds.
Sir, please 3,600 seconds.
So we have 1 divided by 3,600 seconds. So that will be the frequency. So divide 1 by 3,600. What is 1 divided by 3,600? This is
2.7 times 10 exponents minus
so let me 2.778 times 10 to the power what? Minus 4 hertz. Do not run your value to the nearest DP unless you are told to do so. Okay. Okay. So the next question also seeks to find its angular velocity. And because angular velocity omega is given by 2 pi f, this is 2 times 22 over 7, or you can also use 3.142 times 2.778 times 10 to the power minus 4. Yes. Just put them together for me.
Please, I had 1.7462 times 10 exponents negative 3.
Negative what?
3.
Okay. Radian per second. Okay. Radian per second. And lastly, the speed of its free end. V is equal to R omega. The speed of its free end, V is equal to R omega. R, change R to meter. So 6.4 times 10 to the power negative 3 times your angular velocity, which is 1.746 times 10 to the power negative 3, and you are good to go. Just give me your answer in 3 decimal places. 3 dp. Are you ready?
Yes, sir.
What's your answer?
1.117 times 10 raised to the power negative 5.
1.117 times 10 raised to the power minus 5 meter per second. So that's the solution to the question. Okay, try this for me. I'll give you about 5 minutes to do that, then we'll continue. An object moves round. An object moves round a circle of radius 3 meters. An object moves round a circle of radius 3 meters with an angular velocity of 4 radian per second. With an angular velocity of 4 radian per second. Full stop. Calculate I. Calculate I, the frequency. I, the period. I, the speed. Calculate I, the frequency. I, the period of rotation. I, the speed. So I'm giving you 5 minutes to answer this. My time is 10:53. 10:58, I'm coming your way.
Miss Lydia, please, can you go over the question?
Okay. An object moves round. An object moves round a circle of radius 3 meters with an angular velocity of 4 radian per second. With an angular velocity of 4 radian per second. Calculate I, the frequency. I, the period of rotation. I, the period of rotation. And I, the speed. Your 5 minutes
Okay.
has started. 3 minutes more.
Mr. Adria, please, what was the last sub question?
Calculate Mami, the question is on the platform.
Thank you.
Calculate the speed. Fifi Pepper, are you done?
Yes, sir.
Okay, so we'll discuss it together so you mark yourselves. Okay.
Okay.
Angel, are you there?
Please.
Eva,
Miss Adria.
are you there?
Yes, please.
Okay. I wish I can mention all names. You have 1 minute more to go. 1 minute. Okay. Your time is up. So let's discuss it. Okay. Get your red pens, your pencils ready. You are going to mark yourselves. Are you set with your red pens?
Yes.
Okay.
Yes.
So we are to calculate the frequency. What are we given? We are an object moves around a circle of radius 3 meters with an angular velocity of 4 radians per second. Calculate I, the frequency. I, the period. So once I have omega, I have R. Omega is equal to 2 pi F. F therefore would be equal to omega on 2 pi. And this is 4 on 2 pi is 6.286 approximately. Therefore, the expected answer is 0.637. 0.637 hertz. So do the marking. B, the period of rotation. Once I have the frequency, period is just a period. So period is 1 on F. Therefore, 1 divided by 0.637, which would give us 1.57 seconds. Then the last question, the speed. The linear or tangential speed is omega r. Omega is 4. R is 3. Therefore, the speed will be 12 meters per second. Please show by hands those of you who scored everything. If you scored everything, let's see you. Raise up, show by hands. Okay, Lagoji did, Pepra, Leslie, Vida, Yansabuapa. More hands. Okay. 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 So that's good. Thank you. Those of you who scored, yes. So if you had one wrong or two, yes, the solution is there. You can correct yourself. Okay. All right. Then let's continue our discussion on equations of uniformly accelerated circular motion or uniformly accelerated circular motion. Just as we have uniformly accelerated linear motion, our three main equations of motion, namely equation 1, which is V is equal to U plus AT, equation 2, S is equal to UT plus half AT squared, equation 3, V squared is equal to U squared plus 2AS. And sometimes we include this, which is not a major equation, but we usually include that as well. S is equal to U plus V over 2 times T. Equations of linear accelerated motion. We have similar equations under circular motion as well. Okay, we have similar, but here we are equally considering uniformly accelerated circular motion. Okay, and a body is said to be in uniform accelerated motion when the body's acceleration is constant or uniform. So over here, we are also looking at a body moving with a uniformly accelerated, okay, or a body moving with a uniform angular acceleration. So what are the circular motion equation? V here stands for final velocity. U here is the initial velocity. A is the acceleration, the uniform acceleration, and T is the time interval. We have the same equation under circular motion. Under circular motion, this would be omega. V is linear velocity. Under circular motion, that would be angular velocity. So omega 2, meaning final angular velocity, is equal to omega 1, initial angular velocity, plus angular acceleration times time. So this is equation 1 when it comes to circular motion. Equation 2, theta linear displacement. S is linear displacement, and the circular motion, that will be theta angular displacement, is equal to omega 1 times t plus half times alpha angular acceleration times the square of the time. That's equation 2. Equation 3, we have omega 2 squared is equal to omega 1 squared plus 2 alpha times theta. Then this sub-equation can also be expressed in circular motion as theta is equal to omega 1 plus omega 2 divided by 2 times t. So these are the equations of circular motion. So once we have an idea of linear motion equations, we can easily connect it to circular motion and we are good to go. Class, are you okay? Are we okay?
Yes, please.
So these are the uniformly accelerated circular motion equations. Now, in linear motion, usually we are given terms like the body starts from rest. When we are told that the body starts from rest, what does it mean? Body starts from rest. Anybody to tell us the meaning of
It means the initial velocity is 0.
Initial velocity is 0. Under circular motion, we also use the same term. Body starts from rest. Body comes to a stop. Okay? Or comes to rest. We equally use these same phrases under circular motion, just as we have in linear motion. Okay, let's try our hands on this question. What is the angular acceleration? Let me take a shot and drop it on the page as well. What is the angular acceleration Okay. I'm dropping a shot of it, of the question on the page. All right, so it's there. What is the angular acceleration of an object in a circular motion, in a circular path of radius 15 meter with a linear acceleration of 16 meter per second squared? What is the angular acceleration of an object in a circular path of radius 15 meter with a linear acceleration of 16 meter per second squared? So the radius we are told is 15 meter. Then the linear acceleration is 16 meter per second squared. And the question demands angular acceleration. This must be answered within 1 minute. Oheneba, are you there? Are we done? So we move on to the next question. Cadmiel, Crispin, Calvin, Joel, Isaac Carter, Goslar, you are all here. Frederick. And you are quiet. And Aquabina, Matthew. Okay, so what's the answer? Erefa, what's the answer?
1.067 radian per second.
Okay, so this here we use the link between linear acceleration and angular acceleration. A is equal to alpha times r. We are looking for alpha, and so alpha will be A on r. What is A? A is 16 meter per second squared divided by 15. So this would be 1 point. 1 point what?
0.7 radian per second.
Radian per second. Radian per second squared.
10 square. Yes, please.
So I'm sure the question on the minds of a lot of you is that, you see, angular acceleration in 16 meter per second squared, radius in meter. So you are wondering how we can get radian per second squared from this. That is not your problem. Okay, your problem rather must be that, you see, for us to express the SI unit of angular acceleration in radian per second, all other units featuring in the equation must be expressed in SI. So the linear acceleration must be in meter per second squared. The radius must be in meter, and automatically alpha would be in radian per second squared. Okay, so if the given quantities are not in SI, then you cannot express angular acceleration in radian per second squared, meaning that you must convert them in order to do so. So that must be your concern. Please, is there any other question? All right, the next question, question 2. The rim of a compact disc starts from rest, and after 30 seconds attains an angular velocity of 6.6, and after 30 seconds attains an angular velocity of 6.6 revolution per second. Calculate the angular acceleration during the time interval in A. I'm modifying the question. You have to calculate the angular acceleration during the time interval in A. Revolution per second squared. B. Radian per second squared. And C. Degree per second squared. So you have to calculate the angular acceleration during the time interval in A. Revolution per second squared. B. Radian per second squared. And C. Degree per second squared. This is the problem of the day. How many minutes do I offer you to solve this for me? How many minutes?
20 minutes.
Hey, 20 minutes is so much. Sorry, 20 minutes
Please,
is
5.
okay. So let me make it 6. 6 minutes. Okay. 2 minutes for each. Start with. And all hands must be on deck, please. Are we on?
Yes, please.
Okay. We've done 2 minutes, so we have 4 to go. 2 minutes more. 2 minutes. A minute to go. 1 minute to go.
Oh, guy. Oh,
So unmute yourself. Okay, I think your time is up. So let's quickly go through this. Let's quickly go through it so you mark yourselves. We have a lot to do. I want us to finish circular motion as quickly as possible. So we start simple harmonic motion. All right, so the rim of a compact disc starts from rest. So clearly this must tell you that the initial angular velocity omega 1 is 0 because it starts from rest. And after 30 seconds, attains an angular velocity of 6.6. So omega 2 is 6.6 rev per second, RPS, revolution per second. This is within a time of 30 seconds. So we are to calculate the angular acceleration during the time interval in these 3 areas. So first one, here, looking at what we have, we'll use the first equation of circular motion. Omega 2 is equal to omega 1 plus alpha t. Therefore, alpha is equal to omega 2 minus omega 1 divided by t. So omega 2, this is 6.6 minus 0 divided by time of 30 seconds. And our angular acceleration will be, what is 6.6 divided by 30? 6.6 divided by 0.2. So we have 0.2 revolution per second squared. So this does it for the first question A. The second question, I can use the results I had for A to answer B. A's answer is that alpha is equal to 0.2 rev over 1 second squared. The denominator, we have no problem. because it's in seconds squared. But the numerator is what we must convert to radian. So if one revolution is to 6.286 radian, what will be 0.2 rev? Will it be more or less? If 1 rev is equal to 6.286 radian, what will 0.2 give us? Will it be more or less?
Less.
It will be less. So if less, more divide. So 0.2 revolution divided by 1 rev times 6.286. And what is 0.2 times 6.28? Yes.
1.38.
1.38 radian.
Sir, please, it's 0.22, not 0.2.
Okay, so 0.22. Okay. And is the final answer right when we use 0.2?
1.387. 1.3827, sorry.
1.3827. I always say that if you are not asked to run your answer to a certain number of dPs, express it in about 3 dP. Okay. So therefore, we have our final answer for angular displacement, angular acceleration being equal to 1.3827 radian per second squared. Okay. The other way to go is that convert omega 2 itself. Omega 1 is 0. Omega 2, which is 6.6 rev per second to radian per second, and then divide by 30. That would also do it. All right. Then our last answer C. Still, we have no problem with the denominator. It is still per second squared, but the numerator. So if 6.286 radian is to 360 degree, then 1.3827 radian, will it be more or less? Of course, it will be less. So if less, more divide. So 1.3827 divided by 6.286 times 360 will convert 1 point this to degree. Please compute that for me. Calculate that for me. Divide 1.3827 by 6.286 and multiply that by 360. Mommy, are you there? Eva.
Yes, please, we are here.
79.1874.
79.
Point
1874.
So here, because for angles, the least count of angular measurement is 1 degree. I'm expressing angle to the nearest degree. Okay, so this is 79 degree per second squared. That is the result. Please, is there any question? Okay, how many
No,
of
please.
us scored everything? Answers. Raise up your hands. If you scored everything, let's see you. Okay. Okay, that's good. 5 more. 5 of you. Okay. So if along the line you couldn't get something right, please, this is the solution. You can always see it to refer to it. Safam, do you have a question or your hand is still up? Okay. Let's look at centripetal force. Centripetal or centripetal, whatever force. Centripetal force.
Centripetal force.
Centripetal and the younger brother, the elder brother, centrifugal. As for centrifugal, we even do not talk about it because centrifugal force theoretically has been defeated, that it does not exist. The reason why it is seen to be non-existent is that its origin, the origin of centripetal force and centrifugal force is that it's from Newton's third law of motion, that for every action there must be Newton's third law of motion. Class, I'm listening.
Equal and opposite reaction.
Okay. So if a body, Nanayao,
Yes, sir.
your hand is up.
Sir, this is what I was coming to say before I said it.
Okay, okay. So we define centripetal force to be a force that enables objects in circular motion to stay within the circular path. So let's assume there is this body A moving in circular motion. At A, there is a force which is always directed from the object directed towards the center of the circle. And this force we are calling as the centripetal force. But from Newton's third law of motion, for every action, there must be equal and opposite reaction. So if there is a force acting on a body directed towards the center, then from Newton's third law of motion principle, there must be an equal force, equal but oppositely force on the body. And this is what we are calling as centrifugal. So F let me indicate that as FF. The reason why it is seen to be non-existent is that imagine this body at a position A to be a stone tied to a string and weld. Okay, so during the course of welding, this is your hand. Your hand is at the center of the circle. The radius is the string, the length of the string which connects the object to the center. So during the course of welding the object, when the string is cut, okay, when we cut the string, naturally we expect that the moment you cut the string, you take off the centripetal force, because the centripetal force which keeps the object within the circular part is provided by the tension in the string. We'll look at situations of circular motions and what provides the centripetal force. But in the case of a string tied to a stone tied to a string and well, please mute yourself if you haven't. Okay, I'm getting the feedback here. So in the case of a stone tied to a string and well, the centripetal force is provided by the tension within the string. So when you cut the string, you have the tension is no more. If the tension is no more, then it means the centripetal force is no more. Okay. Now, if the centripetal force is gone, we expect centripetal fugal to take over, and so the stone must fall in the other direction of the pair of force. Okay, and since centrifugal is away from the object, we expect the stone to fall away, but that will not happen.
Yes, please. Please, I was saying you are moving a bit too fast.
Okay, then I'll move a bit too slow. Okay. So once we take off the centripetal, we expect centrifugal to take over. So we expect the stone to drop away from the circular part in the direction of the centrifugal. But that will not happen. Rather, the stone will move in the direction of the velocity or the speed. When a body is in circular motion, its speed, the linear speed, v, is always tangential to the radius. And when a line, let me mute all of you before somebody unmutes all of us. Good. So the velocity v of the body or the speed is always tangential to the radius. And when the line is tangential to a circle, the angle between the line and the radius is 90 degrees. So when you cut the rope or the string, the centrifugal force will not, throw away the object in its direction. However, the object will be thrown away in the direction of the speed. And so the big question is that if when a body is in circular motion, there are two pairs of forces, centripetal and centrifugal. When the centripetal was cut, why didn't the centrifugal take over and fall the object in its direction, but it went in the direction of the speed? That defeats centrifugal. So it's a theoretical force based on Newton's third law, but it seems to be non-existent. Even centripetal force itself is also said to be a false force or pseudo force. Pseudo force. This is because for every circular motion, the centripetal force is provided by something else. So let's go into it. So first, centripetal force is the force which enables objects in circular motion to stay within the circular path. So let's give situations of circular motion. 1. When a stone is tied to a string and whirled is tied to a string or rope and whirled, this will demonstrate circular motion. Look at what provides the centripetal force. In this case, the centripetal force is provided by the tension in the rope. So it is the tension that is providing the centripetal force. 2. When a car negotiates a bend, a car, bicycle, athletes, a bend or curve, what provides the centripetal force? Yes, class. In this case, what provides the centripetal force? Anybody? Anybody? No idea. Okay, so the centripetal force which keeps the car or the bicycle in circular motion, Mamia.
The friction between the tire and the road.
Exactly. So the frictional force between the tire and the road surface. So here too, something is providing the centripetal force. 3. The revolution of planets around the sun. What provides the centripetal force here? Yes. What provides the centripetal force in this case? It is Willis.
Gravitational force.
Good. So the gravitational force of attraction between between the two masses or bodies. Then 4. Electron orbiting the nucleus. Electrons orbiting the nucleus. What provides the centripetal force in this case? Yes. What provides the centripetal force whenever electron orbits the nucleus? Leslie.
Please, electrostatic force.
So this is the electrostatic force of attraction or repulsion. Also, you must attract the electrostatic force of attraction between the electrons and the nucleus. And it is of this reason that even centripetal force is also termed as a false force or pseudo force, because in all cases it is being provided by something else. There is something within the system which is providing the centripetal force. Okay. Now let's go into what actually creates the centripetal force. Okay, let me give you a minute. I'm advised to give you water break. So 2 minutes or 3 minutes to drink water and then return. Okay. So I'm start.
Say,
Hello.
this water break is 5 minutes.
Hey, okay, 5 minutes. You go and drink water for 5 minutes. And then come back. We have about okay, 46 now. So when you come, I'll engage you for 10 minutes and then we close the dockets on today's okay, so I'm waiting for you. I'm also observing the same week. Hello. I think our time is up. Are we there?
Oh, sir, please, it's not your time. We'll have it 2
Yes.
minutes.
Hey, then your water is really plenty.
In Mr. Chia.
Okay, drink your water. Okay, so we have about 10 minutes to do. Let me give you something on St. Peter Falls today. which you have to read before tomorrow, okay? So read more about centripetal force. What causes it? Okay, yes, we have connected it to frictional force, blah 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 blah. But there are key elements which account for the reason why centripetal force is directed towards the center. Okay, so read on centripetal force, then why the equation mv squared over r or m omega squared r for centripetal force. Okay, so just read on centripetal force, read on this equation, and we'll continue. I'll continue from there with you tomorrow. Is that okay? Because we have about 8 minutes to end the show. Class, are you okay?
Yes, please.
So I've given you reading assignment. I'll probe first thing tomorrow before we continue with other stuffs. Okay. Oh yeah. So Angel and Eva and the rest of you, Pepra, Kumsin, Cadmiel, and all the rest of you. This is where we draw the curtains on today's meeting. I'll send you assignment to work on, then your reading assignments, do not forget it. Until tomorrow, may the good Lord be with you, protect you, guide you in everything. Bye-bye.
Bye. May the Lord be with you too.
Thank you.